Hello students and welcome. Have you ever noticed that your phone charger gets a little warm when you're using it? Or have you wondered how an electric iron gets so hot just by plugging it into the wall? Well, the answer to all of this lies in a really important concept we're going to study today, the heating effect of electric current. It's happening all around us, and today we're going to understand exactly how it works.
So here's how we're going to do it. First, we'll start with a small mystery about where electrical energy actually goes in a circuit. Then we'll dive deep inside a wire to see the secret life of electrons. After we understand the why, we'll get to the how much with a formula called Joule's law. Of course, we'll solve some problems to get comfortable with the math. And finally, we'll connect everything to the real-world devices that you see and use every day. So let's begin.
Okay, so let's start with something we already know. A battery, or a cell, is a source of electrical energy. Its whole job is to push electrons around a circuit to maintain a current. But have you ever really thought about what happens to all that energy that the battery is supplying? Where does it all go?
To think about this, imagine the simplest circuit possible. It just has a battery and a resistor. That's it. There's no fan to spin, no motor to run, not even a small bulb to light up. The current is flowing, the battery is working hard and using up its chemical energy, but what is that energy doing? It seems to be disappearing. This is the puzzle we need to solve.
Take a look at this circuit here. The battery is continuously supplying energy to maintain the flow of current through the resistor. Now, a fundamental rule in physics is that energy cannot be created or destroyed. It can only change from one form to another. So in this circuit, the electrical energy isn't just vanishing, it's being converted entirely into heat. The resistor will start to get warm, and this, right here, is the heating effect of electric current in its purest form.
So we figured out the what. The electrical energy turns into heat. But now for the more interesting question. How does this happen? To really understand that, we need to zoom in. Way in, and look at what is happening at the microscopic level inside the wire itself.
Let's think of it this way. Imagine you're trying to run down a very crowded corridor at school, maybe during the lunch break. It's not going to be a smooth run, is it? You'll constantly be bumping and colliding with other students. Well, for an electron moving through a wire, it's a very similar situation. So let's break this down step by step. First, the electrons get a push from the battery and they start moving. But the path inside the conductor is not empty, it's full of atoms. So the moving electrons constantly collide with these atoms. Now with every single collision, a tiny bit of the electron's energy is transferred to the atom it hits. This extra energy makes the atom vibrate more and more intensely. And this increased vibration of all the atoms in the wire, well, that's exactly what we experience as heat. So heat is just the vibration of atoms. Okay, now we understand why a wire gets hot. That's the concept. The next question a physicist always asks is, how much? How much heat is produced? We need a way to calculate it. And for that, we have a very important formula. It's time to introduce Joule's law of heating. Now, to get to Joule's law, we're actually going to start with something we've already learned, electric power. Do you remember what power is? It's simply the rate at which energy is used. And we know the formula for it. Power, or P, is equal to the potential difference, V, multiplied by the current, I. Now, let's think about this logically. If power is the energy used every second, then how do we find the total energy used over, let's say, a time t? Well, we just multiply the power by the time. Simple. In our resistive circuit, all of this electrical energy is turning into heat, which we'll represent with the letter H. So our first equation for heat is H equals P times T, which is the same as V times I times T. We're very close now. For the final step, we need to bring in our old friend Ohm's law. We all know Ohm's law very well. V equals I times R. What we're going to do now is take this expression for V and substitute it into our heat equation.
So in our equation H equals VIT, we replace V with I times R. That gives us H equals I times R times I times T. Now if we just rearrange that a little bit, we have I times I, which is I squared. So we get our final beautiful equation, H equals I squared RT. And this, my friends, is the famous Joule's law of heating. So what does this simple formula tell us? It reveals three very important things. First, and this is the most crucial part, the heat produced is proportional to the square of the current. That little 2 is very powerful. It means if you double the current, the heat produced doesn't double, it becomes 4 times greater. Second, heat is directly proportional to the resistance R. Higher resistance means more heat. And third, it's directly proportional to time, T.
The longer the current flows, the more heat is produced. Makes sense, right?
Understanding the theory and the formula is one thing, but to really master it, we need to put it into practice. So now, let's solve a couple of numerical problems together to see how Joule's law actually works.
All right, here's our first problem. Let's read it carefully. We are given that 100 joules of heat is produced every second in a 4-ohm resistance. We need to find the potential difference, V. So, what do we have? H is 100, T is 1, and R is 4. Now, we know V equals IR, but we don't have I. But we can find I using Joule's law. Let's rearrange H equals I squared RT to solve for I. That gives us I is the square root of H divided by RT. Now let's put in the numbers. I is the square root of 100 divided by 4 times 1. That's the square root of 25. So the current I is 5 amperes. Now we're at the final step. We just use Ohm's law, V equals IR. So V is 5 amperes multiplied by 4 ohms, which gives us our final answer, 20 volts.
Let's try one more. This one's a little more direct. An electric iron has a resistance of 20 ohms and takes a current of 5 amps. We need to calculate the heat developed in 30 seconds. So let's list our given values. R is 20, I is 5, and T is 30. Here we can use Joule's law directly. H equals I squared RT. Let's substitute. H equals 5 squared times 20 times 30. So that's 25 times 20, which is 500. And 500 times 30 is 15,000. So the heat developed is 15,000 joules, or we can say 15 kilojoules. See? Once you know which formula to use, it's all about careful substitution.
So we've done the theory, we've done the math. Now for the really fun part, connecting all of this to the real world. This heating effect isn't just a topic in your textbook, it is the principle behind so many technologies we use in our homes every single day.
Let's look at a classic example, an electric heater. Have you ever noticed that the element, the coil part, glows bright red hot, but the connecting cord that you plug into the wall barely gets warm? Think about it. They are in series, so the same current, I, is flowing through both of them. So why the huge difference in heat? The answer is in the R from our formula. The heater element is made of an alloy like nichrome, which has a very high resistance. The cord, on the other hand, is made of copper, which has a very low resistance. Since heat is directly proportional to R, the high resistance element produces a lot of heat and glows, while the low resistance cord produces very little heat. Another brilliant application is the electric fuse. A fuse is a very important safety device. It's really just a small piece of wire made from a special material that has a low melting point. Now, if for some reason the current in the circuit becomes dangerously high, what happens? Because H equals I squared RT and I is now very large, the fuse wire gets extremely hot, extremely fast. It gets so hot that it melts, and when it melts, it breaks the circuit, stopping the flow of current. This simple little device acts like a bodyguard, sacrificing itself to protect your expensive TV or computer from damage. Before we finish, let's quickly clear up 2 common points of confusion. First myth: higher voltage means more heat. This is not always true. The fact is, heat depends on I squared times R. You need a current flowing through a resistance to generate heat. Just having a high voltage is not enough. Second myth: why is the current squared? Let's just quickly remember our derivation. We started with power equals V times I. Then we replaced V with I times R. So our equation became I times R times I. You see, there are 2 I's in there. That's why we get I squared.
All right, we've covered quite a lot today. Let's just take a moment to pause and summarize the most important points that you should take away from this lesson.
So, what are the crucial points? First, whenever current flows through a resistor, electrical energy is converted into heat energy. Second, the reason this happens is because of collisions between the moving electrons and the atoms of the wire. Third, we have a fantastic tool to calculate this heat, and that is Joule's law, H equals I squared RT. And finally, this heating effect is not always a waste. It is an inevitable consequence of current that we have cleverly learned to use in devices like heaters, light bulbs, and fuses.
And I'll leave you with a final question to think about. We've talked about some simple applications. But if this heating is an unavoidable part of any electric circuit, how else can we use this effect to our advantage in modern technology? Think about it. It's a perfect lead-in to our next topic, where we will discuss electric power in more detail. Thank you for your attention today.